Every hydrogen cycle starts the same way. A press release, a rendering, a groundbreaking ceremony, hard hats, smiles, headlines that say milestone achieved. And every time this happens, the industry quietly treats it as proof that hydrogen is finally working. But history shows something very different. In hydrogen, execution risk doesn't disappear when construction begins. It actually concentrates. The moment a project moves from planning into execution is the moment risk becomes real, irreversible, and expensive. This is why execution risk, not technology, not policy, and not ambition, dominates hydrogen outcomes. The recent groundbreaking of a new electrolyzer project in Feuchtwangen, Germany, is a perfect illustration of this pattern. Not because the project is flawed, and not because it will necessarily fail, but because it sits exactly at the point where most hydrogen projects enter their most dangerous phase. Groundbreaking is not success. It is the transition from theoretical viability to physical reality. And in hydrogen, that transition is where most projects quietly die. Hydrogen has no shortage of technology. Electrolyzers exist, compressors exist, pipelines exist, storage exists, none of this is new. What is new is the attempt to assemble all of these components into tightly coupled, capital-intensive systems that must operate reliably, continuously, and economically under real-world constraints. That is not a technology challenge. That is an execution challenge. And execution is where hydrogen is least forgiving. When a project breaks ground, its degrees of freedom collapse. On paper, assumptions are flexible. In execution, assumptions harden into steel, concrete, contracts, and schedules. Design margins that looked generous in spreadsheets suddenly feel thin when interfaces don't align. Contingencies that felt conservative shrink rapidly when delays stack. This is why hydrogen projects don't usually fail loudly. They fail quietly between phases, through delays, redesigns, renegotiations, and creeping cost overruns that slowly erode confidence. Execution risk dominates hydrogen outcomes because hydrogen systems are interface-heavy. Electrolyzers are not standalone machines. They sit at the intersection of power markets, water systems, cooling systems, compression systems, storage systems, transport systems, and offtake systems. Each interface introduces coordination risk. Each interface introduces schedule risk. Each interface introduces counterparty risk. And each interface multiplies failure modes. A hydrogen project doesn't need everything to go wrong to fail. It only needs one interface to underperform at the wrong time. This is where many observers misunderstand the significance of groundbreaking announcements. Breaking ground does not mean that interfaces are resolved. It does not mean that offtake is secure. It does not mean that utilization will be achieved. It does not mean that operating assumptions will hold. It simply means that capital is now exposed. And once capital is exposed, recovery becomes increasingly difficult. The hydrogen industry often borrows mental models from renewable power, especially solar and wind. But hydrogen execution risk behaves very differently. A solar project that is delayed still produces electricity when finished, and that electricity has a liquid, fungible market. Hydrogen does not. Hydrogen demand is narrow, specific, and often contractual. Missed schedules don't just increase costs. They threaten offtake commitments, certification eligibility, and financing structures simultaneously. Time is not neutral in hydrogen. Time is destructive. Execution risk also dominates hydrogen outcomes because hydrogen projects are deeply sensitive to utilization. A small drop in utilization has an outsized effect on cost per kilogram. During execution, utilization risk increases, not decreases. Grid interconnection delays reduce run hours. Commissioning delays push projects into different power price regimes. Contractual ramp-up assumptions clash with physical ramp-up realities. These effects compound. A project that looked viable at 60% utilization on paper can quickly become fragile at 45% utilization in reality. And execution is where those losses occur. Groundbreaking ceremonies rarely discuss these dynamics, but lenders certainly do. Banks do not finance hydrogen projects based on technology novelty. They finance them based on execution credibility. They ask uncomfortable questions. Who controls the interfaces? Who absorbs delay risk? Who pays for redesigns? Who guarantees performance? Who bears degradation risk? And most importantly, who takes the loss if utilization underperforms? These questions become unavoidable the moment construction begins. This is why execution risk dominates outcomes even in regions with strong policy support. Germany has incentives, industrial demand, and engineering expertise. None of that eliminates execution risk. In fact, complex regulatory environments often increase it. Permitting delays, grid constraints, and certification uncertainty introduce timing mismatches that compound execution risk rather than reducing it. Policy can lower cost. It cannot eliminate friction. Another reason execution risk dominates hydrogen outcomes is that hydrogen systems are path-dependent. Early decisions lock in future costs. Pressure choices determine compression energy. Cooling design determines efficiency losses. Storage configuration determines operating flexibility. These decisions are made early, often before full operational data is available. Once construction begins, changing them becomes expensive or impossible. This is why execution is not just about building what was designed, it is about surviving the consequences of early design assumptions. Many hydrogen projects fail not because the technology didn't work, but because the system couldn't tolerate deviation. The grid delivered power differently than expected. Water availability fluctuated. Cooling loads were underestimated. Maintenance windows were longer. Degradation occurred faster. None of these issues are surprising individually. What is surprising is how little margin hydrogen systems have to absorb them. Execution risk is the mechanism through which these small deviations accumulate into failure. The industry often celebrates first-of-a-kind projects, but first-of-a-kind is precisely where execution risk is highest. Novelty increases interface uncertainty. Supply chains are immature. Contractors lack experience. Performance guarantees are weaker. Replacement parts are scarce. Learning curves are steep. Every deviation becomes a lesson, but lessons are expensive when capital is deployed at scale. This is why execution discipline matters more than innovation in hydrogen. Execution risk also dominates outcomes because hydrogen projects sit between industries. They are not fully power projects, not fully chemical plants, and not fully infrastructure projects. This creates coordination gaps. Power developers underestimate process complexity. Industrial players underestimate grid volatility. EPC contractors struggle with hybrid scopes. Responsibility blurs. Accountability diffuses. These organizational frictions manifest during execution, not during planning. Groundbreaking events mark the transition into this risk landscape. They should be treated as caution flags, not victory laps. The real work begins after the cameras leave. Commissioning schedules tighten, cash burn accelerates, stakeholder patience shortens. This is where governance matters. Projects with clear decision rights, disciplined change control, and conservative scheduling survive. Projects without these traits drift. This is also where the difference between bankable and fragile projects becomes visible. Bankable hydrogen projects are boring. They favor proven designs, they limit interfaces, they sequence capacity carefully. They prioritize operational stability over peak efficiency. They assume delays and plan for them. Fragile projects chase optimization. They assume best-case utilization, they compress schedules, they rely on future policy clarity. Execution exposes these differences mercilessly. The Feuchtwagen project, like many others breaking ground across Europe, now enters this critical phase. Its success will not be determined by electrolyzer efficiency or press coverage. It will be determined by execution discipline. How interfaces are managed, how deviations are handled, how conservative assumptions prove to be, whether governance holds under pressure. These are not questions that can be answered today. They are questions that will be answered over years. This is why hydrogen outcomes cannot be predicted by announcements alone. The industry is full of announced capacity. It is short on operating capacity. The gap between the two is execution risk. Every project that closes that gap successfully does so not through brilliance, but through discipline. For developers, this has profound implications. The most important decisions are not the ones that generate headlines. They are the ones that reduce execution fragility. Conservative load assumptions, realistic ramp-up schedules, clear interface ownership, robust contingency planning. These choices rarely appear in marketing materials, but they determine survivability. For investors, the lesson is equally clear. Hydrogen projects should be evaluated not on ambition, but on execution structure. Who bears risk when things go wrong? How much margin exists? How sensitive is the project to delay? What happens if utilization is lower for longer? These questions matter more than technology roadmaps. For policymakers, execution risk explains why incentives alone do not guarantee outcomes. Subsidies can enable projects to start. They cannot force them to finish. Reducing execution friction requires infrastructure coordination, grid clarity, and realistic timelines. Otherwise, policy accelerates exposure without reducing risk. Hydrogen's future will not be decided by how many projects break ground. It will be decided by how many survive execution. The industry does not need more announcements. It needs more projects that cross the valley between construction and operation without collapsing under their own complexity. This is the quiet reality behind today's hydrogen headlines. Execution risk dominates outcomes because hydrogen is a system problem, not a component problem. And systems only reveal their weaknesses when they are built, stressed, and operated. If you are a developer, consultant, or investor working in hydrogen, this is the phase that matters most. Understanding execution risk is not optional. It is the difference between participating in the hydrogen transition and watching it from the sidelines. At H2 Hub by Renee Energy, this is exactly what we focus on. Not hype, not announcements, but the execution realities that determine whether hydrogen projects reach commissioning, operate reliably, and survive under real-world stress. If you want to understand where projects actually fail and how to avoid those failure modes, that's where the real work begins. Hydrogen does not fail because it is impossible. It fails because execution is unforgiving. And until the industry treats execution risk as the dominant factor it truly is, the gap between ambition and reality will remain. That is why execution risk dominates hydrogen outcomes. And that is why groundbreaking is the beginning of the test, not the proof that hydrogen has passed it.